Determine whether there is a function, g of x, which is differentiable for all values of x, has g of x greater than 1 for all values of x, and has the area under the curve y equals g of x over the interval 3 to 6 equal to 2. Okay, so we're talking about area. This last statement here can be interpreted as saying a definite integral from 3 to 6, g of x dx is equal to 2. And we're trying to determine whether such a function exists. So what would be an acceptable answer? Well, you could say yes and say, here's a function g of x that does this. Or you could say no, and here's why I know there is no g of x. Okay? But first we have to sort of reason, what do we think is going to happen? Now we know our function g of x is always going to be greater than 1. Okay? So if we imagine 1 out here, the function's somewhere up here. Doesn't matter exactly. Now they tell us an area over 3 to 6. Right, so this area in here, they're saying needs to be 2. But hold on for a second. Since it's greater than 1, inside this area is this red area of height 1 and a width of 3. This area should already be 3. And yet we're saying that somehow this bigger area is 2? That doesn't seem right. So I might say, well, I don't think there is a g of x. Okay? But proof by picture rarely counts. You could probably get away with it in certain situations, but we have stronger tools at our disposal, so let's go ahead and use them. Okay? This is exactly the sort of situation where the mean value theorem for integrals can help us. Okay? So we'll say no. Okay? Let's use the mean value theorem for integrals in a proof by contradiction. So how does proof by contradiction go? You assume the opposite of what you want to actually show, and you show that just from that assumption, using logic, deduction, formulas that are already established, that leads to a contradiction, an impossible mathematical result, like 1 equals 0. Okay? So suppose we could somehow find such a g of x. Okay? Now we want to use the mean value theorem for integrals. What do we need? Well, we need a closed interval. 3 to 6 would work great. But we need our function to be continuous on that closed interval. And they never once said continuous in the question. So are we on the wrong track? Is there something wrong? No. They tell us our function is differentiable for all values x. Okay? What we need to do is remember that if a function is differentiable at a point, that means it's continuous. There's a consequence. If you're differentiable at a value a, you must be continuous at a. Okay? The opposite result is not always true. Take a look at, say, the absolute value function. But we can say, since g is differentiable, which we'll just abbreviate as diffable, okay, it is also continuous. For all values of x. Okay? So, where can we go from there? Well, if it's continuous, we can say g is continuous on, I think it's 3 to 6 is the closed interval we need. So the mean value theorem, you can write for integrals, but we already said it's going to be for integrals, so we could probably just get away with MVT. So the mean value theorem for integrals applies. What's the conclusion from there? There is a, now usually I say, see, I'm going to just switch things up. I'm going to say there is a B. Sometimes people get hung up on notation that somehow C is a special number. So we're going to say there is a value b, okay, in between 3 and 6, we could write it this way. You know, b is greater than 3, less than 6. We could write it that way. So that g at b is equal to 1 over 6 minus 3, the endpoints of our interval, and then the definite integral. Okay, but the definite integral is 2. So g at b is 2/3. So 2/3 is g at b, but we also know that all values of g need to be greater than 1, not less than 1. Okay. So 2/3 is greater than 1? I don't think so. Contradiction. Okay, this is an impossible statement. Okay, now, all of our work was fine. We applied the mean value theorem for integrals correctly. Okay, we got the conclusion. All our calculations in here were fine. The only thing that was not built on solid logic was our assumption. Suppose we could find such a g of x. So if we've reached an impossible conclusion, a falsehood, it must have been because we started with a falsehood. Okay. So our assumption that g exists is false. Thus, we see that no function g can satisfy the given conditions.